people during this special time are talks like what we're hearing today. One can go to a conference, number one, without paying registration, and learn about a field. And there are opportunities all over the world every day. And so by looking outside your field at your interests, I found that's been one of the best guides for where we've taken our group and where our students and postdocs have ultimately found what they're interested in. I think students and postdocs ought to know that you're not restricted to what you did in your training. You've heard how there's an arc, in the trajectory of what you do in science, and you can change. One of the wonderful things about academics, if that's your goal, is you can change fields very dramatically. What we do now and what Professor Claridge did with us is absolutely nothing like what I did as a graduate student, is even in a different phase of matter. And we heard a beautiful lecture from Professor Kim in our first round of ACS Nano lectures about how one moves from one area into another, and is driven by that I think curiosity sums up everybody's efforts. Any last thoughts that each of you has for the students and postdocs out there that you'd like them to know?
I think I'd like them to know that this is a tough year, but that it will get better. Because I think that in talking to some of the students, it's a pretty discouraging time. The job market got bad for a while, but there are fluctuations. This is an especially bad one, but fluctuations that restrict what you're doing in one area can cause you to focus in a new area. So try to find opportunities to use the restrictions to do something new. I think that's the best thing to do right now.
Very good. And following on Professor Liu's point about learning to write papers and so forth, I'll add that we put together a series of editorials and videos because there are things one learns as an editor that no matter how smart or intuitive you are, you don't really know until you see the other side. And so since all our editors are also scientists, we've tried to tell everyone else what we've learned about how to write a cover letter, how to respond to referees, and so forth. And so, do have a look at those and some of the Publishing 101 videos at ACS as a way to learn about those, the mechanics and logic of writing papers and editing papers and so forth. So, well, thank you very much to our panel.
Thank you, Paul.
And congratulations. And so let's move on to our third and final talk. Delighted and honored to introduce Professor Shelley Claridge of Purdue University, where she was an associate professor in the chemistry and biomedical engineering departments. As you heard, Professor Claridge got her PhD at Berkeley, and then worked with us at first Penn State, and then UCLA. Along the way, she's picked up many awards, including the DARPA Director's Fellowship and Young Faculty Award, the NSF Career Award, the DuPont and 3M Young Faculty Awards. And it's my very great pleasure to introduce her, where she'll be talking today about patterning interfaces near the atomic limit, lessons from the cell membrane. Professor Claridge, Shelley, the floor is yours.
Thank you. All right, I'm going to share my screen. And everything got quiet when I did that. So can you guys hear me?
Yes.
Awesome. Okay, perfect. So it's a huge pleasure to be here today. I'm so glad to be able to talk with all of you. It was wonderful to be able to meet the other speakers today for the first time this week. Today, as Paul said, I will be telling you some about my group's work in patterning surfaces near the atomic limit using lessons from the cell membrane. And I think some of the ideas that you'll be hearing about may be fairly new.
Sorry, there's a little bit of a delay. At least the screen is not yet sharing.
Oh, wow. Okay.
There you go. Now it's on. on.
Oh,
It's
okay,
on.
so now I know where to watch for that. That may mean that there's about a 20-second delay. So we'll see what that means for my slide advancing, and I will keep an eye on that screen over there. All right. So I think that the ideas that I'll be talking about today may be a little off the beaten path for many people in the audience. So I wanted to actually start in a slightly more familiar place, which is with a talk that many of you have either read or encountered. That's Feynman's famous talk, "There's Plenty of Room" at the bottom. And what I'm seeing is that there is at least a 15-second delay in my slide advancing. So imagine with me a slide about Feynman. Feynman gave this talk in 1959 to an audience of physicists. And he was talking about a set of ideas relating to controlling the structure of very small things. When Feynman says small, he means very small. In fact, he means at the atomic scale. And I think actually, maybe this is my fault. Okay, that was, let's see how long that takes to show up. When Feynman talks about small, he means actually very small. He means on the scale of atoms. And he swears that this is going to be very useful for a whole variety of technological applications. He gives this talk in 1959, and essentially nobody pays attention for the next 20 years. So over the course of 20 years, that talk was cited a total of 7 times, right? So let that sink in, given what you know now about the talk. And after about 20 years, something beautiful happened. After about 20 years, scientists invented the scanning tunneling microscope. So suddenly it was possible to build structures at the atomic scale. What you would be seeing, if you could see my second slide, would be the word IBM written in, there we are, okay, partly. You'll be seeing the word IBM written out of xenon atoms on a nickel surface, and they've been organized using a scanning probe tip to form the acronym IBM. So at this point, people began to become more excited about the possibility of building at the atomic scale, and people began to revisit Feynman's talk. In this talk, he talks about a whole variety of different topics, including biology. He discusses biology a lot, which you'll see on the next slide. And what I want to highlight about what he said about biology is that he's primarily focused on DNA and RNA. So you'll see the text in a second, and I'll highlight, actually, I'll just go ahead and put in all the highlights so you can see them when you get there with me. He talks a lot about DNA and RNA. He also mentions proteins and peptides several times. Okay, you're not going to be able to see the cursor moving either because the slide just showed up. We'll get through this. So he also talks about proteins and amino acids. And the thing that he's interested in is biology's ability to design complex architectures using small numbers of atoms. He mentions specifically that DNA encodes a bit of information about the cell in about 50 atoms. He mentions the fact that proteins are designed from a sequence of amino acids. Okay, so Feynman talks a lot about DNA and proteins, but he's more or less silent on the subject of other biomolecules like lipids and carbohydrates. Now, correlation does not equal causation, but decades later, when researchers went back and started to build up the emerging nanobiomaterials field, this set of trends, I would argue, was replicated. So if you did a Google Scholar search today for DNA and nanotechnology or proteins and nanotechnology, you get on the order of 1 million hits, whereas you get many times fewer hits for either lipids and nanotechnology or carbohydrates and nanotechnology. So part of what I'm going to be arguing today is that these classes of biomolecules that are a little off the beaten path represent sort of undervalued stocks in the nanobiostructure field. These are places where there's opportunities for a great deal of growth in both science and technology. Lipids are primarily what I'll be talking with you about today. This is what my group does. And the other thing that I want to persuade you, because we use lipids in a sort of unconventional sense, is that you're already very comfortable with the use of biological structures in very non-biological ways. I'm going to do that using the example of DNA. Most of you are probably familiar with the fact that DNA in your body forms a double helix. Some of you may know that the helix diameter is about 2 nanometers. What you may or may not be aware of is that in your body, since DNA is meant for storage, it gets packaged. So DNA gets wrapped around charged proteins called histones. The histones in turn organize into structures called chromatin, which form parts of your chromosomes, which you can see at the bottom of the slide. The dimensions of chromosomes are huge relative to the helix. So 1400 nanometers in width here, clearly even longer. And yet, when we use DNA in nanotechnology applications, we use it in a different way. We use very short DNA strands, 50 to 100 bases typically. We often add chemical functional groups like thiols that let us attach nanocrystals. This was something I did in my graduate work, not that paper, but that general idea. We form the DNA into very non-biological shapes, the star, the smiley face. And all of these things we now think of as very normal, even though they're totally outside the biological function, and basically all they share is the sequence-specific base pairing. Now it turns into molecular recognition. So we get a whole new set of function by using this design principle in a different way. So what I hope to persuade you of is that that's also something that we should be considering with other classes of biomolecules like phospholipids. A lot of people encounter phospholipids in freshman biology and don't return to them after that. So we'll start by reviewing a little bit about phospholipid structure. The slide will show up in a minute. Perfect. In freshman biology, what you probably learned is that your cell membranes, like you're seeing on the left, are made up of a lipid bilayer, like you're seeing in the center. You probably drew the lipid bilayer, sort of like you see it in the center, with a circle and two sticks. The circle represented a hydrophilic head group, and the gray sticks represented hydrophobic tails. The thickness of the lipid bilayer was about 6 nanometers. This is a great cartoon from a freshman biology perspective. It's distilling the essence of a complex system into something that's easy to draw, but it also sort of overlooks some important aspects of chemical complexity in nature's design of this boundary that separates the cell from everything else around it. And we can see this if we think about the problem of transmembrane protein structure. Something that biologists have started to appreciate in the past several years is the incredible complexity that goes into transmembrane proteins. What you'll see in a moment on the right is the structure of the potassium ion channel. This sits across the cell membrane. You can see that depicted as 2 lines at the top. And it's difficult to imagine that a structure like that derives the foundation of its form from something that's binary, just hydrophilic and hydrophobic. And in fact, if we went back and drew this cartoon more correctly, what we would see is that this boundary in the biological system is not binary. There are actually several polar functional groups that form the transition between the nonpolar core and the aqueous environment that makes up most of you. If we look at the structure of the phospholipid head group in a little more detail, what you can see is that the base functional groups at the bottom are esters. The esters have strong dipoles, but they don't have to maintain a charge. And that's important because they're sitting right next to the nonpolar core, where it's very difficult to charge nanostructures. The 2 ester linkages are asymmetrically mounted on this 3-carbon glycerol backbone. And then the next position is occupied by a phosphate, which has a very low pKa, meaning that it's easy to ionize. Okay, that's important because it's also fairly near the nonpolar core. The phosphate in turn is linked to an ammonium group. So this pair of charges together forms a substantial dipole on the order of 25 to bi. And for scale, the dipole on water is a little under 2 to bi. So this is enough that each lipid head group can orient something like 15 water molecules. And biologically, that turns out to be important in proton transduction along the surface of the cell membrane. So there's an incredible amount of chemistry built into this boundary between the hydrophobic core of the bilayer and the polar periphery. And that's across a length scale of just 6 nanometers. Okay. That length scale for the chemical boundary, I think, is very important because what we find across all sorts of problems in synthetic material design is that chemical boundaries at 5 to 10 nanometer scales are important in function and difficult to achieve. So in the last talk, you were hearing about the importance of surface conduction at scales less than 10 nanometers, right? So those surface layers are incredibly important. In electronics more broadly, the 7 and 5 nanometer nodes are after upcoming manufacturing targets. And the goal there is to design boundaries between materials that conduct electrons well and those that don't. These boundaries are very difficult to achieve precisely at that scale using lithographic processes. Now, boundaries in chemistry are important also in materials for organic photovoltaics. So in that case, it's a different kind of boundary. It's a boundary between materials that conduct positive charges and those that conduct negative charges. That's based on something called the exciton diffusion limit, which tells you about how far charges can transfer before they fall back down to the ground state. You need to separate them, which means you need precisely ordered materials with boundaries at that length scale, which turns out to be 5 to 10 nanometers for many classes of organic materials used for energy conversion. Biology has 5 to 10 nanometer boundaries as well beyond the cell membrane. This is also very much the length scale of ligand clustering for cell surface receptors. And in all of these cases, the need for structure starts at 5 to 10 nanometer scales, but it often extends to much greater length scales, microns, even millimeters. Now, going back 2 slides, right, I just told you that the cross-section of the lipid bilayer was about 6 nanometers. Okay, but in the applications I've described here, you'd actually like access to both kinds of the chemistry in some structured way across the surface, whereas in the lipid bilayer, the molecules are stacked like this. Let's see, oh, this is just not gonna work. The molecules are stacked, so the hydrophobic part of the membrane is sequestered. It's not available to the environment. That would sort of imply that what we would like in terms of designing chemical boundaries at interfaces wouldn't so much be a lipid bilayer per se, it would be more like a repeating cross-section of a lipid bilayer, which from a biological perspective is a very strange surface chemistry. All right, biology is built on assembling to sequester hydrophobic parts of molecules. That's true not only in membrane structure, but also in the folding of proteins. And now we'd just like to lay all of that structure out on the surface, and the slide may be with us momentarily, or it may not. That's interesting. This is really, okay. Well, you'll see momentarily a cartoon of a repeating cross-section of a lipid bilayer on the surface. And actually there we go. And this looks like a very strange surface chemistry, but it's actually a sort of surface chemistry that's effectively been known going back to Feynman's world, in the physics and physical chemistry community for a large number of years. So in fact, it's been known that molecules with long alkyl chains can lie down on graphite and other layered materials. This turns out also to work on molybdenum disulfide. I don't know if it works in all of the materials that we saw in the second talk, but certainly it works in many cases. In the case of graphite in particular, there's reasonably good epitaxy between the zigzag alkyl chain backbone and hexagonal graphite lattice. That's something you're seeing on the left. There are also lateral interactions between the alkyl chains, and in the monolayers seeing here, this 1012 pentacosadienoic acid, there's also hydrogen-bonded carboxylic acid dimers that are stabilizing the lamellar median. And I apologize, I'm using my hands, but I think you're not going to see my pointer moving at the appropriate time. So you can look back and forth at me and at the slides if that's convenient. Okay, in this monolayer of 1012 pentacosadienoic acid, you'll notice if you look at the molecular structure that down the middle, there's a group highlighted in yellow. That's a polymerizable group. So it can be polymerized using UV irradiation. And that provides a conjugated E9 polymer backbone. You can see all of the parts of this process in scanning tunneling microscopy. In the upper right-hand corner of the image, each line that you're seeing is a row of lying down molecules. You can see the formation of the E9 or polydiacetylene polymer backbone. It's the bright stripe or apparent protrusion in the STM image, which you're seeing based on a combination of electronic delocalization along the polymer backbone and a sort of angstrom atomic scale protrusion in the monolayer that develops during polymerization. Now, classically, in the scanning probe community, going back to the importance of surfaces and charge transport, this is a chemistry that's been of interest in the context of molecular electronics. The E9 shares electrons between the carbons, so in principle, it could act as a molecular wire. But our group's interest has been in understanding the extent to which we could use these 1 nanometer wide functional patterns that are very precisely and very straightforwardly created on the surface as a means of generating surfaces that would look sort of like a repeating cross-section of a lipid bilayer, and that would create precisely defined chemical boundaries at few nanometer scales that we could use for all of the applications that I was describing before. All right, if that were the case, you could then envision using the surface chemistry, which you'll see in the animation when it shows up, to organize other structures like inorganic nanocrystals. In a moment, you'll see an animation of gold nanowires that appear and then deposit on the surface. 1 second to show up, because at some point it's just going to be hard. There we go. Here come the nanowires. Well, here sort of come the nanowires. Okay, there we go. So the nanowires, we can envision using the chemical patterns on the surface to organize them and to address the other sorts of applications that I talked about in my introductory slides. And so in that vein, my group thinks about at least 2 general classes of questions that you'll see on the upcoming slide. Perfect, this is better timing. One set of questions are fairly fundamental questions, and these relate to chemistry in confinement. I think a lot of people in nanomaterials are comfortable with the idea that in something like a quantum dot, confinement is important. So the smaller the quantum dot is, the more confinement electrons experience, and that changes their energy levels in ways that you can read out via photoluminescence. That's usually described in what's called a particle in a box model. And so I tend to think of these questions about the chemistry of organic functional groups in confinement as functional group in a box problems, describing the related effects that are also important outside of inorganic structure. In the monolayers that we're using, flexibility could also be important. So the monolayer is non-covalently adsorbed to the surface, and there would be the possibility for structures to move around a little bit. That's also something we need to understand if we're going to use the monolayers on the surface. The other set of questions that we ask are practical ones. So, what are the functional groups that we need? Can we scale this sort of ordering that you see in the STM image here with a scale bar of 50 nanometers? Could we scale that up to micrometer or millimeter scales? What would that need? What would that mean? Another set of practical questions relate to the fact that the monolayer is non-covalently adsorbed. You see that in the image just next to the STM image. The monolayer is non-covalently adsorbed, so could it really survive solution processing and other things you might reasonably want to do in preparing a device? Additionally, we've heard a lot about wearable electronics, other applications that require a flexible surface that's not necessarily crystalline. So could we take this surface chemistry and use it on other substrates that would be of interest for things like wearable electronics or scaffolding cells? So I'll tell you a little bit about a couple of fundamental questions, a little bit about scaling, and then mostly I'll talk about ways that we use the surface chemistry. The first question that we wanted to ask in the context of fundamental questions related to ionization. Many of you will have had organic chemistry and you've thought about things like pKa values for common organic functional groups. Here we have in the monolayer a carboxylic acid, which you'll see it's trying. It'll be with us in a minute. Perfect. Well, you see carboxylic acids, which in something like acetic acid has a pKa just under 5. It's a weak acid, but it ionizes. And our question was, if you put these functional groups in a striped phase on graphite, is their chemistry the same? How does confinement change that? How does the chemical environment matter? That's something we need to know if we want to use them for building. We asked that question using what's called a contact angle titration, where we're putting a droplet of aqueous buffer on the surface. And if we ionize the carboxylic acid, removing a proton to form the carboxylate, the surface gets more hydrophilic, which you're seeing in the upper left-hand corner. The droplet is spreading out, and we measured the angle between the line tangent to the drop and the surface. That's our contact angle. So if we have a more hydrophilic surface, we expect that value to go down. If we do a titration from pH 3 to pH 13, which you're seeing on the right, you can see that the contact angles are decreasing for PCDA, which is the gold lines. And you can see that the midpoint of that titration curve is around pH 9.5. Okay, from an organic chemistry perspective, that's interesting, right? This means that the weak acid is no longer really acting like a weak acid in the conventional sense. So it's been very changed by its chemical environment, and that's something we need to be aware of if we want to use these to design other structures at the interface. Other sets of questions that we ask related to things like the role of flexibility. I think I'm actually going to go straight one slide further to make sure that we're there by the time we need to talk about the drawing. The question that we asked had to do with flexibility in the monolayer and how that was determined by the position of the polymer backbone. The head groups we envisioned might be able to move around in a monolayer of this type, but we envisioned that they would be tethered by the position of the polymer backbone. So perhaps the closer that your tether was to the head group, the less flexibility the head groups would have. So my student made an isomer of PCDA where he took the diene and put it in the 4-6 position right next to the head group. And we looked at what happened when the monolayers polymerized. Mostly the paper was about wetting, but the reason that I'm telling you about it today is that it taught us an important lesson about the role of atomic scale motion in these monolayers and how they interact with the environment. Because what goes on during polymerization is sort of an atomic scale tug of war. You can see on the left that as the diene is rehybridizing to form the enine, that the stripe is narrowing just a little bit where that gold line is. It's a small change, but what it means is that one end of the molecule or the other end of the molecule needs to move a little bit relative to the surface. If we think about which end of the molecule wins that tug of war based on segmental interaction energies, for the molecule on the left, the energies are similar, meaning that half the time we'd expect this end to move, half the time we'd expect this end to move. Whereas for the one on the right, there's a pretty clear winner in that long terminal chain segment. So what we find is that means for the molecule on the right, the head group always moves in a way that breaks the carboxylic acid dimer, and it makes that functional group more available to interact with other substances near the interface. So that was an important design principle for us. The last thing I'll say very briefly is about the role of the phospholipid head group. We'd been interested in how the chemistry of the phospholipid head group might be useful in mediating the polar-nonpolar transition. And what we found is that the phospholipids, when they're formed into striped phases, unlike the carboxylic acids that we showed earlier, which form a lying down structure, the phospholipids form what I would think of as a sitting phase. So you're seeing here the phosphate is next to the graphite. The amine protrudes a couple of atomic diameters into solution. And what that ends up meaning is the amine acts more like it's in a normal polar solvent environment. So this is a very atom efficient way of making the transition from the nonpolar surface to doing weak acid and base chemistry just adjacent to it. All right. I want to make sure we have time to talk about scaling and applications. So we'll say just a couple of words about that. The images that you've seen so far have primarily been at very small scales, less than 100 nanometers. What we've found over time is that we've developed devices and protocols that allow us to scale ordering up to micrometers or even hundreds of micrometers. What you'll see in a moment is an SEM image that's showing long-range molecular alignment in a monolayer of this type, which you're seeing based on linear defects that form in the monolayer based on that change in molecular configuration that we talked about a couple of slides ago. Diene rehybridizes to form the enine, and that makes a defect we can see. And we can use that defect to understand something about the structure in this monolayer that's just a few atoms thick. Part of how we do this involves thermally controlling the sample during the assembly of the molecules. And we can do that either in Langmuir films, by bringing the graphite down on top of the Langmuir film on water, or we can do that using a prototype roll-to-roll transfer operation where we have a heated copper disc that rotates the surface slowly through the monolayer in order to pick up the striped phase. Using the heated roller design, we're able to create very long-range ordering indeed, which you'll see in this SEM image that will come on the screen in a minute. What you'll be seeing in this image is a set of lines that cut through at large scale. Those are defects in the graphite surface. And you'll be seeing some smaller cracks similar to the ones that you saw on the previous slide. Those indicate the long-range molecular alignment in the monolayer. Okay, the scale bar on the image that you'll see is about 20 microns. So overall, the alignment in this case was nearly 100 microns. I'm going to let it catch up so you can see the image. I'll take a drink. There we go. Okay, so now you're seeing the monolayer, you're seeing the cracking defects in the monolayer and the long range alignment from the upper right to the lower left of the screen. In some cases, you want just long range ordering in general, but in other cases, what you might actually want is geometric control over the shape of your pattern on the surface. And so one of the other things that we've been doing is creating methods for microscale geometric patterning of striped phases. The image that'll come up on screen next is also a large area of a graphite surface. It will appear pixelated. And you'll also see a large defect in the corner down there. When the pixelated image shows up, we'll start. This is a little difficult. If we zoom in on what appears to be a pixelated image, what we'll see is that the pixelation is in fact a square pattern in the monolayer on the surface, and that each square is made up of many, many small domains of striped phase that are organized in epitaxy with the surface. I think I should probably wait for it to catch up because it'll be hard to understand what I'm saying if the images aren't on screen. Okay, so here you're seeing what appears to be a pixelated image. And you're seeing in the corner the thing that appears to be a mountain. That's actually a big multi-layer step edge in the graphite surface. In the background, you're seeing this sort of speckling, and in a few moments, the slide will advance so you can see that that's actually a square pattern. Okay, well, it skipped 2 of the slides, and now we're on microcontact printing. So what you're seeing in the lower right-hand corner is a smaller set of the square patterns. We use this technique to prototype the ability to make striped phases also out of more complex head group chemistries like carbohydrates, which you're seeing in the lower left-hand corner. Here we made nanometer-wide stripes of phosphoinositol, so nanometer-wide patterns of carbohydrates on the surface, which is an important step toward being able to design interactions with cells on these surfaces. Okay, now we're going to move on and think about ways of using the surface chemistry more explicitly. So what you'll be seeing in a minute is sort of a schematic of the ability to use the striped phase, where the head groups are very much like nanocrystal ligands, as a means of organizing and perhaps growing inorganic nanocrystals on a surface. There have been a couple of data points that said you could deposit clusters of things like gold on a surface, but we were interested in whether you could use the anisotropy of the pattern as a means of organizing in anisotropic nanostructures directly. So what you're seeing in the lower right-hand corner is the idea that you might organize a nanowire, but a problem that you might encounter in that regard is that the nanowire might bind across the surface, become kinetically trapped, and be unable to reorient to its lowest energy configuration in full alignment with the striped phase. My student did these experiments using ultra-narrow gold nanowires, the type that had been reported previously in the literature. These use olealamine as a ligand, which forms cylindrical micelles around the gold structure in solution. You can see at the bottom, there's a TEM image showing the diameter of the nanowire is 1.5 to 2 nanometers. And in solution, these wires form bundles. Okay, so the problem with that is that then if you expose the gold nanowire solution to a surface, what you get is bundles of wires on a surface. Okay, now we're actually advancing much faster. All right, what you're seeing in the upper right-hand corner is a bundle of gold nanowires exposed to a bare graphite surface, and in the AFM image, you have bundles of nanowires just deposited as they are. So there's no way to address the individual nanostructures. What we wanted to understand was how the striped template might be able to change the assembly behavior at the interface. So what you'll be seeing in a moment is gold nanowires deposited on a striped phase of a phospholipid. Part of what you'll be seeing is bundles of nanowires very much like the ones that you're seeing on this slide. Okay, and then in some areas, you're seeing something very different. You're seeing wires that are well separated, they're very parallel, they're very straight. And if we look more closely in an AFM phase image at what's going on the surface, that underlies that transition, what we'll be seeing is that the wires remain bundled in areas where the template is aligned like this, and the bundles of the wires are aligned like this. So the wires remain bundled if they cross the template axis, but in areas where the wire bundle is aligned with the template axis, the wires separate. There's another slide that was meant to, there we, okay, and we went right past that one. Anyway, I apologize, I am having very little correlation between how long it is between when I press the button and when the slide actually comes up, and sometimes it's 30 seconds and sometimes it's 3 seconds. All right. We began to ask questions about chemically why this was occurring on the surface, and what we began to find is that the dipoles in the phospholipid head groups were important. We said earlier that there's this 25 divided dipole between the two functional groups, and it turns out that that seems to be what induces the repulsive interaction that separates and straightens the wires. If Ashlyn does this sort of deposition on a striped phase where there's just an amine as a head group, what she finds is that the wires more or less align with the template, but they don't separate in the same way. So they don't become as straight or as organized. If she does the experiment again with a set of different molecules with head group dipoles, she finds that all of those experience this repulsive interaction. And then there was something else that turned out to be important too that we should have thought about, but surprised us nonetheless. And that's a seasonal difference. When we began to do these experiments, it was summer, and we saw organization like what you're seeing at the bottom. As we headed into winter was when we began to first see really nice alignment and ordering of the wires. And to a surface chemist, what that actually means is that water in the atmosphere is important. Okay, many people in audiences that I talk to have encountered related challenges in their own work. So it's fun to look around the room when I put this slide up, usually because I see people shaking their heads and doing like this. A lot of people have experienced the same pain in different ways. So knowing that water in the atmosphere is important, Ashlyn began to control that parameter. So in summer, the environmental humidity is around 50%. Clearly, that's not ideal for absorption. In the winter, in Indiana anyway, it's between 10 and 20%. This is where she sees nice ordering of the wires. And so she thought perhaps the game was to remove as much water as possible. So she pulls vacuum on the surfaces overnight. She finds that that increases absorption, but not ordering. So the wires absorb to the surface, but it appears that they can't reorient. We began to ask why that was the case using molecular dynamics simulations, and found that around 20% relative humidity, which you're seeing as a 4-to-1 ratio of water per lipid head group, sort of in the middle of the dynamic simulations, we're making a transition from discrete clusters, which you see in the upper right-hand images, to a contiguous channel of water along the lipid head groups. And it's very easy to imagine that might be important if the behavior we observe has to do with orientation of the head group dipoles. It turned out that other components of the reaction solution were also important. I think I'll largely skip these so that we're staying on track. But there are other components of the reaction solution like olealamine that turn out to be important. Ashlyn's testing that here, but I'll show you what the result is when it gets with us. The olealamine in the reaction solution is important because now we have a nanometer wide water channel along each row of head groups. The olealamine is an amphiphile, and when it is exposed to the surface through the reaction solution, it forms a micelle. That's important because it can protect the water that's on the surface. If we think about the implications of having this nanometer wide dipole array on the surface with the olealamine around it, and what that would mean for a gold nanowire approaching the surface, if the head group dipoles have a substantial component normal to the surface, what we might expect is that a wire encountering that dipole array might begin to polarize, and it might do that actually across its short axis. This is not what we normally expect from nanowires. Normally, we think of the long axis as the stronger polarization axis. Certainly, that's true for plasmonics. But in this case, it's a reasonable first step. And what that would produce is repulsive interactions between the wires, very similar to the ones that we were observing. There we go. So here what you're seeing in the lower left-hand corner is two wires absorbed to the dipole arrays on the surface, and that they polarize across their short axes. Okay. All right. This brings up an important point about self-assembly using polar chemistry in a non-polar environment that I think is one of the most powerful things that comes out of this unconventional uses of lipids at surfaces. I'm highlighting that here with a cartoon. Normally, if you make a chemical template out of polar functional groups, charged functional groups, the range through which it interacts with its environment in water is defined by something called the Debye limit, which is about a nanometer in aqueous buffers. So that channel that's shown in blue represents the range through which that stripe can impact its environment. What that means in practice is that if you have something like a gold nanowire in the environment, even if it's 10 nanometers away, that may be too far away to interact with the template. But now our system does something different because the hydrated head groups sit not in an environment like water, which has a dielectric around 80 in bulk. They sit surrounded by alkyl chains in cyclohexane, which has a dielectric around 2. What that ends up meaning is that the distance through which charges interact increases to nearly 30 nanometers. If we draw that again in the context of our cartoon, 30 nanometers would mean that a wire in the center of the screen would interact with other wires potentially 4 or 5 stripes away, which it looks like you will see momentarily. All right, so what you're seeing in the peach semicircle is a diagram of the Bjerrum volume, if you will, at the surface, implying that a wire in the center should be able to interact with a wire on the edge of the screen across a distance of about 30 nanometers. And in fact, if we go back to that AFM image we saw earlier, the distance between the 2 wires that you're seeing based on that black bar is almost exactly 28 nanometers. So this means that the wires are interacting with each other over much, much longer distances than they normally would. And that's powerful for generating assembly effects at the surface. Okay, so I think in the interest of time, I'm going to skip a couple of slides so that we can talk about transferring this patterning to amorphous surfaces. In a lot of the talks, I think in this series, you've been hearing about wearable electronics, in which many different materials are used, but common ones are elastomers, things like PDMS. And we were curious whether it would be possible to take the chemistry that we're able to achieve on graphite and to transport it to an amorphous surface like PDMS. This looks like a good option in the cartoon I'm showing. The PDMS looks very much like the graphite. It's easy to envision that transfer occurring. But if you looked at an AFM image of PDMS, what you're seeing here is that it has a pore structure or mesh size around 10 nanometers. So if we look at that in comparison with the striped phase at the top, that chunk of striped phase at the top, okay, chunk of striped phase at the top would more or less sit in one of the pores, but we order the monolayer over distances of hundreds of nanometers, and then we're able to polymerize the ordered monolayer. So perhaps the polymer backbone would be able to stabilize the structure during transfer. And in fact, we find out that that's the case. What we find is that the chemistry of PDMS curing is a useful thing that we can take advantage of. When PDMS is cured, it involves a reaction that you're seeing in the bottom center of the screen between silicon-hydrogen bonds in the crosslinker and carbon-carbon double bonds or vinyl grooves in the base polymer. When we carry out this cross-linking reaction in the presence of a polydiacetylene monolayer, what we find is that covalent bonds are formed to the polydiacetylene, and that means that we're able to remove the monolayer more or less intact. If we look at AFM images of the surface after transfer, they look very much like a hybrid of the striped phase on graphite and the pore structure of the PDMS. And at microscopic scales, we can see evidence of the vacancies in domain structure that you would be able to observe on the monolayer prior to transfer. Reacting with polydiacetylene backbone induces torsion, which I think you'll probably briefly see in a molecular model that looks like it's partly on the slide and partly not. The torsion is inconvenient in the terms of preserving order, but is also useful in the context of characterization. Because to characterize these nanometer-wide patterns on PDMS, we're going to have to move to a whole different tool set. Previously, at microscopic scales, we've used scanning electron microscopy for characterization. That's not an option on PDMS because it's not conductive. But what we are able to take advantage of now is optical properties of the polydiacetylene backbone. It's been known for many years that polydiacetylenes have a red form and a blue form. The red form, at least, is fluorescent, And for whatever reason, either because of quenching on the graphite or because we formed the blue form on graphite, if we put a monolayer on graphite in the fluorescence microscope, what we get is this. It's very boring. But after we transfer the monolayer to PDMS, we're able to observe domain structure, which you'll see in an image that will appear momentarily. I don't even know how to do this. In the transferred monolayer structure, what you'll be seeing in a moment is long, narrow domains that are oriented in epitaxy with the graphite. And if we do this sort of imaging with a spectral detector, we're able to build up a spectrum for the monolayer on the surface that tells us it's consistent with the polydiacetylene. So there's an excitonic peak, there's appropriately offset vibrational sidebands, and the intensity of fluorescence turns out to be different for different molecules. So if we pattern two different kinds of molecules side by side on the surface, like you're seeing on the right, we can see differences in the fluorescence intensity that tells us where regions of different molecules are. Okay, so that's important if we want to make chemical patterns of multiple types on a surface for applications. We'd also like to understand things like the orientations of the polymer backbones on the surface. So not just where is our pattern, but how is it oriented if we want to align multiple layers. It turns out that the polymerization is, the fluorescence is polarized along the polymer backbone. And so we can introduce, we can do polarization filtering on the emission channel, and we can selectively turn on and off different domains in the monolayer based on the molecular orientation of the polymer backbone. So we're able to get a surprising amount of chemical information out of the monolayer based on, really just a few atoms thick layer of organic matter on an amorphous surface. Okay, I think there's two slides that I kind of really want to show you here, and we'll skip through as we're able to. We wanted to understand whether we could use the chemical patterns after transfer. After all, there's a little bit of disordering that's occurring on the surface, but we wanted to understand, for instance, could we still achieve ordering of nanowires? So what you'll be seeing in a minute when the slide advances is in the upper right-hand corner, an AFM image where there's the pore structure of the PDMS, there's areas of bare PDMS, and then in some areas you can see that the structure of the surface is clearly different and that there's long, narrow features. Those are gold nanowires that have been deposited from solution, and they deposit selectively on areas that are functionalized with the monolayer, and the wires align and separate and orient in much the same way they do prior to transfer. So we're able to really take advantage of the chemical structure on the surface to do new useful work. We can also do reactions with molecules. Here we're using rhodamine red, and use that to elaborate the monolayer, to add in chemistries that might not be convenient to build into the polydiacetylene monomers themselves. The very, very last thing that I want to show you is an example of using the fact that we can pattern an amorphous surface as a means of scaffolding cell growth. Your cells grow into tissues based on a combination of chemical and mechanical cues from the extracellular matrix. And we were curious whether we could use the rows of head group chemistry and the mechanical benefits of the polymer backbone to change the ways that cells grow on surfaces. So what you'll see on the next slide is that in the left-hand column, cells essentially don't adhere to or proliferate on PDMS. But if we do the same experiment with PDMS with a striped phase, the cells expand individually, and if we expose them to differentiation media, we get the formation of myofibers, which orient along the direction of the monolayer on the surface. Okay, so overall, I hope I persuaded you, in spite of some technical issues that I didn't anticipate, that there's still plenty of room at the bottom. And in fact, there's whole classes of biomolecules that I would argue are still underexplored, that we should be able to use those structures in new ways, like the phospholipid stripe phases that I showed you, not only to achieve nanometer resolution patterning at surfaces, but also to generate hierarchical assembly, to generate scaling and geometric control, and even to take these nanometer-wide patterns and transfer them to completely different surfaces on which the molecules themselves would never assemble. From a fundamental perspective, I hope I've persuaded you of the importance of chemical boundaries, that this is a place where we really have a lot to learn from biology, and that the design of the phospholipid head group takes careful account of the exact position of a functional group relative to that boundary to generate a diverse palette of function from a very limited basis set of functional groups. that using these functional groups, polar functional groups in a non-polar environment, has the potential to be very powerful, and that really this is just the tip of the iceberg. What I've shown you today is the results from just a few very common phospholipids, and in fact, in biology, hundreds and hundreds of structurally different amphiphiles make up cell membranes, all of which I would argue we can put to use. That just leaves me to thank many, many people. So the graduate students who did the work, which you'll be seeing in a moment on the next slide. We should thank the technician for our lab, Dave McMillan, who helped design a lot of the instruments and equipment that we use in the group. The work doesn't happen without money, so we'll thank all of our funders, ACS, NFF, 3M, DARPA, DuPont, Showalter Foundation. Thank all of you for staying. I know it's very late Beijing time, and I'd be happy to take any questions.
Terrific. Thank you, Shelley. We have a series of questions. Let me see if I'm able to share now. They're working, yes. Great. So the first question is, Professor Claridge, a very inspiring talk. Those are very interesting fundamental discoveries. What do you envision for the applications of these self-assembled systems?
Right, exactly. And I think one of the directions that we're certainly moving in is the slides that I was showing at the end, and I apologize that they were not as visible as one would have liked to see. But one of the things that I think is really unique about the ability to pattern on the nanoscale on soft surfaces is, for example, the ability to scaffold cell growth. So that's one of the areas that we're interested in. It's also possible then to scaffold the assembly of inorganic components. So for instance, if you wanted to lay down patterns that would cause assembly of inorganic nanostructures for a wearable device or for sensors, those are also options. I think the real strength of this system is actually the chemical diversity that's possible to embed in the patterns. I think, I was emphasizing that there are hundreds of structurally different amphiphiles, and one of the things that's really special about amphiphiles is the broad range of head group chemistry in comparison with other biological building blocks where you have, for instance, 4 DNA bases or 20 amino acids. You have the ability to position many different functional groups in different places. So you can design nanostructures to control interactions with specific receptors on a cell surface, for instance.
And then we had a question from Alice, and that is, where did you get your artistic sense to put together such beautiful graphics and slides?
Thank you so much for that comment. That's an interesting question. So in part, I think some of these skills I started to develop in Paul's group, actually. So I was writing a review article. I think that was one of the first times that I'd really started to think seriously about graphic design and composition. Some of the images that I was showing you today were actually put together with help from a friend of mine who is better at Illustrator than I am. And so Sonia Kim was very helpful in putting together things like the protein that's spanning the lipid bilayer. And I would encourage actually broadly that scientists make use of people who understand graphic design, because I think for work that we do, for instance, it's usually very much outside people's experience. And so the ability to visualize something in a nice graphical form can be important in understanding. So. Yeah.
No, I completely agree with that. In fact, I'll note that graphic that you made for the front piece of the cluster assembled materials review that really helped start that field. You wrote the review for ACS Nano. That became the key graphic that was used for the second decade of the National Nanotechnology Initiative in the U.S. So, a graphic that really says a lot can go a very long way, and that's a great.
And I guess actually one other thing that I'll say bouncing off of that is that I also teach general chemistry. And I think something you learn in general chemistry is about simplifying to get across the core meaning, which is something that I always find to be important in trying to find ways of expressing more advanced science, because I'm usually expressing it to people who have a research background that's slightly different than mine. And I think that's figuring out what are the elements that you can take out is often an important part of thinking about how to communicate science.
Yeah, that's a great point too. I think the most successful oral exams for the graduate students out there are the ones where the students translate the questions from the professors into general chemistry or general physics or fundamental engineering concepts, and then answer them at that level where everyone in the room understands that the student has a deep knowledge and can simplify important questions. Well, let's go on to the next question. So, dear Professor Claridge, very inspiring talk. Those are very interesting fundamental discoveries. What do you envision for the applications of those self-assembled systems?
Okay, did we just answer this one a couple of questions ago?
Yeah, looks like it got.
I mean, I also care very much about.
I see. No,
applications.
Right. Yeah, somehow these got reversed. It looks like I read number 2 first. Yeah, my apologies. Professor Claridge, amazing. Thanks for sharing these beautiful results. When you moved down to build 1 nanometer electronic devices, did you run into the surface conduction issues that Professor Zhang Liu mentioned?
It's an interesting question. So
early in California.
It's difficult all the way around the world, as it turns out. Yeah, no, that's a great question. We're just sort of moving into some early electronic measurements, but I think based on what we're seeing in terms of ionization, you'd very much expect to see surface effects. I mean, I think surface conductivity is something that impacts all sorts of materials. I mean, you see skin effects, for instance, in standard electronics, but I think for us, even moving a functional group a couple of angstroms away from the interface changes how it ionizes, which to me would point to the dramatic impacts, actually, of exact positioning of functional groups in terms of controlling the passage of electrons or protons, other charged particles. And I think some of these things are questions that biology is well positioned to address.
Let's get to the third question. What a nice talk. Nanometer self-assembly on surfaces. How large an area is uniform, and what's the biggest challenge for this method?
Okay, yeah. So and this is something else that I think was kind of lost in the slide transition. So one of the SEM images we're showing that we can get long range ordering over length scales of perhaps 100 microns or more. Using the roller-based transfer method, we can get domain sizes 10,000 microns squared. And I think actually that probably the thing that leads to the ordering on those very large scales is actually pre-ordering in the Langmuir film. We don't know that for sure, but I think the challenges would be, to do this, on a scalable way. Really, we'll need to do this in a way that doesn't involve Langmuir films. I think that those are something you can scale up to a certain extent, but certainly if you want to do roll-to-roll processing on rolls that are 8 feet wide, there's got to be some other way. I think what we've achieved is orders of magnitude larger scales than existed before us. But when you talk about frustration and how it drives new things, that's something that we're frustrated about as well.
Mm-hmm. Well, before going on with your certificate, I'll say with all the difficulties you had, you did so well during this, and it reminded me of a jazz concert I went to many years ago at the Greek Theater in Berkeley, which is an outdoor theater, and it was a windy day, and there were 3 performers, and one of them just loved the fact that everything was chaos. There's Claude Bolling, the pianist, performing, and I won't say who the very famous flautist was, but he got angry and sort of yelled at the crowd and yelled at the wind and couldn't stand the fact that, even though it was jazz, he had to improvise. And then the guitarist sort of made his way through. But today you prove yourself to be Claude Bolling. So thank you so much for going through with wonderful elan in today's talk. And so we're delighted to have you as an ACS Nano Rising Star in Nanoscience and Nanotechnology. We'll look forward to the forward-looking perspective that you're writing, and also to have your wisdom as part of our Rising Star board. And I want to thank all 3 speakers today for these really wonderful and insightful talks, and also for sharing their thoughts and careers with us. Next week, we have these speakers in the Advanced Electronics and Applications talks. as well as a candidate for IEEE president, who will talk about what he'd like to do as in that position. And I think I have one more in which our our next Rising Star lectureships will be from Yufan Hu at Beda, Ada Goki at National University of Singapore, and Maria Lukatskaya at ETH. And September is something of an ACS Nano month. As you'll see, we have editors Paula Hammond and Andre Nell and Yan Lee all speaking through the rest of the month, as well as our frequent contributors, Song Jin and the folks you heard about next week. And so that brings our ACS Nano Rising Star Lectureship and our volume 21 of ICANX to a close. Thank you all for joining. We had well over 300,000 attendees today, and it was another terrific Friday here. So in Beijing, good night. In America, good morning. And in Europe, we'll let you continue with your day. So thank you all very much.